level. Calibrated airspeed is equal to true airspeed, lower than true airspeed, more than true airspeed. So, if you are flying in ISA conditions at mean sea level, the calibrated airspeed shown by your airspeed indicator will be equal to the true airspeed of your aircraft. Now, all your pressure instruments are designed for operating in ISA conditions, International Standard Atmosphere conditions. But in everyday life, sometimes we have conditions which are warmer than ISA, conditions which are colder than ISA. So in such disparate situations or conditions, there will be differences between calibrated airspeed and true airspeed. But when conditions are equal to ISA conditions, the true airspeed at which you are actually flying in the air mass will be equal to the calibrated airspeed shown to you. Okay, so that's why same as 2s2. Now, let's say you are flying at mean sea level, but the pressure, atmospheric pressure at mean sea level is lower than standard atmospheric pressure 1013. What will happen? The airspeed indicator, which is a pressure instrument, will have less atmospheric pressure for registration. If less atmospheric pressure is available for airspeed indicator to use as an input, the output given by it will also suffer. The output given by it will also be that much less. Okay, you may be flying at a constant true airspeed of let's say 200 knots, but the atmospheric pressure available at mean sea level is lower than the standard pressure. As a result, pressure available for airspeed indicator for use will be less, and by that much amount, the output shown, the airspeed shown by the speed indicator will also be less than true airspeed. Okay, so true airspeed will be 200 knots, but the speed shown to you will be 180, 150, less than 200. Okay, so but when you are flying in atmosphere, standard atmospheric conditions, calibrated airspeed will be equal to true airspeed. A turn indicator is built around a gyroscope with 2 degrees of freedom, 1 degree freedom, 3 degree freedom. So correct answer is a turn indicator has 1 degrees of freedom. Next. Main cause of error in direct reading magnetic compass is parallax, turning error, acceleration error. So your magnetic compass is subject to two errors. Turning errors, which happens when you turn your aircraft around the northerly heading, southerly heading, and acceleration deceleration errors, which happen on easterly and westerly headings. Okay, so the correct answer here is always select turning error as your answer. Considering MMO, which is maximum operating Mach number, and VMO, that is maximum operating speed, velocity, the captain of a pressurized aircraft begins his descent from a high flight level in order to meet his scheduled time of arrival. He decides to use maximum speed any time of the descent. He will be limited by what? So, now there are two speeds, VMO and MMO. So first let's discuss VMO. Now we all know that your airspeed indicator is nothing but a pressure instrument. Like I said before, this airspeed indicator or pressure instrument uses uses dynamic pressure to represent calibrated airspeed, to show calibrated airspeed or indicated airspeed. So whatever reading that we are getting from the airspeed indicator, the indicated airspeed or indicated airspeed corrected for position and pressure error, calibrated airspeed, it's nothing but an indirect representation of your dynamic pressure. Okay, so that is your calibrated airspeed or indicated airspeed, the job done by your airspeed indicator. Now what happens when, let's say, you are flying at mean sea level at a calibrated airspeed of 100 knots, at a calibrated airspeed of 100 knots. So at the dynamic pressure there, the dynamic pressure when you fly at mean sea level of at calibrated airspeed of 100 knots is equal to, let's say, 500, is equal to 500. Okay, now what is this dynamic pressure? Dynamic pressure is nothing but the pressure exerted on your aircraft by the forward movement of your aircraft, right? We have normal static pressure. I'm sitting here. the pressure that is acting on my body is the static ambient pressure, stationary pressure. But when I start moving, there will be additional pressure acting on my body called impact pressure or dynamic pressure. Now, when a body like aircraft moves at tremendous speeds, fast velocities, the pressure created by the impact will be will be very much. Okay, will be very much, and that dynamic pressure will impose loads on the structure or fuselage of your aircraft. So if you are flying at a calibrated airspeed of 100 knots, the dynamic pressure created is, let's say, 500. Now let's say you go to a higher altitude of 5,000 feet. Now when you go to higher altitudes, atmospheric pressure surrounding that altitude or available at that altitude will decrease. As you go to higher and higher altitudes, atmospheric pressure decreases. That means less atmospheric pressure will be available for your airspeed indicator to use to register. So if less pressure is available for registration, so the output, which is your calibrated airspeed or indicated airspeed shown by your airspeed indicator, will also decrease. Okay, so when you go to higher altitudes, automatically calibrated airspeed will decrease. It will become 80, and the dynamic pressure is, let's say, becomes 400. Okay, when you go to, let's say, another 8, go to a higher altitude 8,000 feet, again atmospheric pressure will be lesser, so the calibrated airspeed register will be 70, the dynamic pressure generated will be 300. Okay, so on and so forth. As you go to keep going higher to higher altitudes, atmospheric pressure decreases. As a result, calibrated airspeed will also decrease. Now you may be flying at a true airspeed of true airspeed of 150 knots, let's say. At mean sea level, a true airspeed of 150 knots, you get a calibrated airspeed of 100 knots. You maintain this true airspeed of 150 knots and you go to 5,000 feet. But what happens to your atmospheric pressure? It decreases, and therefore calibrated airspeed has decreased. The true airspeed, the true airspeed of your aircraft is the same, 150 knots. Just because calibrated airspeed has decreased from 100 to a new airspeed of 80 knots doesn't mean your aircraft has decelerated. It only means that the atmospheric pressure surrounding your aircraft has decreased. The dynamic pressure acting on your pitot tube has decreased. It just means that. Now, if you want to maintain, if you desire, if you wish to maintain the same calibrated airspeed as you go to progress to higher and higher altitudes, what will you have to do? The thing you will have to increase the true airspeed of your aircraft. Why? Now, when you increase the true airspeed of your aircraft, the forward velocity, the forward motion of your aircraft will increase, will accelerate, will get accelerated, right? So, the more the forward velocity of your aircraft, more will be the dynamic pressure acting on your aircraft, impact pressure acting on your aircraft. So, if more dynamic pressure is acting on your pitot tube, that means the calibrated airspeed proportional to that dynamic pressure will also increase. More dynamic pressure, more calibrated airspeed registration, right? So if you want to maintain this 100 knots at 5,000 feet as well, what will you have to do? If you want to maintain this 500 knots, correction, 100 knots at calibrated airspeed at 5,000 feet as well, you will have to increase the true airspeed of your aircraft from 150 knots to a new speed of, let's say, 180 knots. You will have to add power, increase the forward speed of your aircraft. Okay. Now, you want to continue maintaining this 100 knots calibrated airspeed at even higher altitude of 8,000 feet. What will you do? You will you will have to again increase your true airspeed by more numbers, because as you go to 8,000 feet, again the atmospheric pressure at that level will be much lower than the atmospheric pressure at mean sea level. Correct? So now the true airspeed of your aircraft will be 200 knots. You will have to increase it even more. Okay? So this will keep going on. Okay, and the dynamic pressure will be same, 500. 500, 500. Okay, so so this keeps going on. Now you can keep doing this, keep increasing the true airspeed of your aircraft, 250, 300, 350, so on and so forth. As you keep increasing the true airspeed of your aircraft, the calibrated airspeed will also go on increasing, 150, 170 as required, 200. Proportionally, the dynamic pressure will also increase 600, 700, 800. Now there will come a point where the you will reach or you will achieve or you will attain the maximum dynamic pressure that can be imposed on your aircraft. Okay, maximum dynamic pressure you will reach a point uh, where you will reach a point where you will have attained the maximum dynamic pressure. Now, what is maximum dynamic pressure? That is nothing but maximum loads that can be imposed on your aircraft. Okay, so this maximum dynamic pressure will be equal to some maximum. It will be equal to some maximum calibrated airspeed. It will be equal to some maximum calibrated airspeed, right? If you increase, if you go beyond the speed, calibrated airspeed, the dynamic pressure will also increase, and that will cause structural damage to your aircraft. So this is the first limitation with respect to your speed, airspeed. Okay, the maximum calibrated airspeed beyond which you cannot go, because if you do that, the dynamic pressure or the loads acting on your aircraft will be tremendous, will be too much. And this maximum calibrated airspeed will be called your VMO, beyond which you cannot fly. The speed beyond which you cannot fly your aircraft. Okay, so this is the first condition, first limitation, VMO, dynamic pressure calibrated airspeed. Now the second condition is MMO, the maximum operating Mach number. Now what happens when your aircraft exceeds the speed of sound? When your aircraft exceeds the speed of sound, what happens? Shock waves develop around your aircraft. Shock wave will develop around your aircraft. Now the slowest speed at which speed of sound is achieved, that speed is called critical Mach number. That speed is called critical Mach number. The speed at which the first or the speed at which the local speed of sound is achieved. That is called critical Mach number. Now, once you cross this critical Mach number or the local speed of sound, shock waves will develop. These shock waves have unfavorable results for your aircraft. You will have tremendous drag and loss of lift. Loss of lift. What is the consequence? The consequence of this is that your aircraft will suddenly pitch down. Okay, the nose will suddenly drop. Okay, it will pitch down. Next things, the boundary layer of your aircraft, the boundary layer of your aircraft will start separating from the surface, and it becomes turbulent. Now, what these conditions, boundary layer separating from your aircraft, the layer getting turbulent, is synonymous with stall condition, right? We have all learned about stall condition. If you have flown, you must have definitely practiced this stall maneuver in your flight. So stall condition, these conditions are similar to stall conditions. So what happens when boundary layer gets detached from the surface of your aircraft? The surface starts vibrating. The control surface starts vibrating. They become ineffective, and you may soon exceed the angle of attack threshold. Okay, and you may still you may exceed the angle of attack threshold and reach the stall speed of your aircraft, where there will be total loss of lift. So MMO. So in conclusion, MMO resembles that maximum Mach number beyond which you cannot fly. Okay, you're prohibited or you must not fly because you may encounter this unfavorable conditions. And if your aircraft is not designed for supersonic flights, for fast high-speed flight, then you may enter a stall condition, which is very unsafe. Okay, so this is MMO. So now you are limited by VMO and MMO, both VMO and MMO. Now when you are flying at, when, let's say this is your altitude x-axis, altitude, y-axis altitude correction, and x-axis is speed. VMO is nothing but calibrated airspeed, maximum calibrated airspeed proportional to maximum dynamic pressure. So a particular calibrated airspeed will always produce the same dynamic pressure. 100 knots, 500 dynamic pressure. 170, 700 dynamic pressure. So that amount is fixed. So your VMO is going to remain constant with altitude. Your VMO speed remains constant with altitude. You go to higher altitudes, it's the same calibrated airspeed. Come down to lower altitudes, same calibrated airspeed. What about maximum operating Mach number? So maximum operating Mach number value decreases as you go to higher and higher altitudes. Okay. Now the place where both coincide, the place where both VMO is equal to MMO. Okay. This is called change over altitude or crossover altitude. So you will be limited. What does this picture tell us? You will be limited by VMO at altitude lower than this. That is, at lower altitudes, you will be limited by VMO at lower altitudes. And above this level, you will be limited by MMO at high altitudes. Okay. So when you are descending from a high level to a lower level, you will be first limited by MMO, and after a particular level, you will be limited by VMO. So the correct answer is initially you are limited by MMO because you are descending from high level, and then VMO below a certain flight level. Next. A turn indicator is an instrument which indicates rate of turn, how fast you are turning. Rate of turn depends upon bank angle, yes. Aeroplane speed, yes. Not aeroplane weight. So, bank angle. Now let's say the bank angle of your aircraft is 10 degree. With a 10-degree bank angle, you are able to make a turn like this. Okay. You increase the bank angle to 20 degree. What happens when you increase the bank angle to 20 degree? You will be able to make this turn at much smaller radius, quickly, faster. Okay, with 10-degree bank angle, you will make this big circle. With 20-degree bank angle, you will be able to turn your aircraft around much quickly. Okay, so this small circle is made. If you increase your bank angle further, let's say 30 degree, 40 degree, again you will be able to turn your aircraft much quickly, more quickly. Okay, so this is happened. So bank angle, as bank angle increases, you will be able to turn aircraft around much faster. Okay, because what happens when bank angle increases, when you increase the bank angle, what you are doing in turn is that you are increasing the centripetal force. You are increasing the centripetal force of aircraft, which is the inward directed force, which is nothing but the inward directed force directed towards the center of the circle. The horizontal component of your lift increases, and this horizontal component of your lift will pull you towards the center of the circle, and you will be able to make that turn much faster. Second is aeroplane speed. What happens with aeroplane speed? Now with the speed of your aircraft, this is the center. Let's say the speed of your aircraft is 100 knots. With 100 knots speed of your aircraft, this speed is nothing but the forward speed of your aircraft. You will be able to make a turn like this, let's say 100 knots. Okay, you increase the speed of your aircraft to 200 knots. What happens when you increase the true speed of your aircraft to a new speed of 200 knots? Your turning radius will increase. So 200 knots, you will make a turn like this. The turn radius will increase. You will require larger area to turn your aircraft around because the speed of your aircraft is very fast. The forward speed is very fast, so that speed will try to pull your aircraft straight ahead instead of pulling it around, or instead of turning it around. It will try to stretch your aircraft or force your aircraft in the straight forward direction like this instead of turning it around to the left. So faster the speed of your aircraft, more forceful will be your forward velocity, forward motion. Slower the speed of your aircraft, easier or more convenient it will be for you to turn your aircraft around the because small speed means small kinetic energy. Okay, so let's say your speed of aircraft is 50 knots, 50. So you will be able to turn your aircraft much quickly like this. So speeds and bank angles determine your rate of turn, how fast you are able to turn your aircraft. Next, an airborne instrument equipped with a gyro, 1 degree of freedom, and a horizontal spin axis. So 1 degree of freedom and a horizontal spin axis is DGI artificial horizon turn indicator. So it's turn indicator which has 1 degree of freedom. Aircraft is accelerating in the north hemisphere. Very important. You are in the north hemisphere. Heading west. What will happen to your compass indication? So now your magnetic compass is subject to acceleration and deceleration error. Okay, which happens on the headings of east and west. Now, when your aircraft is heading westerly and you accelerate your aircraft on westerly heading, what will happen to the indication of magnetic compass? Magnetic compass will show a turn towards the North Pole. You are in the North Hemisphere, it will show a turn towards the North Pole. Apparent turn, false indication towards the North Pole. So instead of showing an accurate direction of 270, it will show any direction which is more than 270, 300, 320, whatever. When you decelerate your aircraft, you decrease the forward speed of your aircraft, when you decelerate it on a westerly heading, what will happen? The magnetic compass show an apparent turn towards the opposite pole, that is the south pole, towards the south pole. So instead of showing a direction of 270, it will show a direction which is towards the south pole. So any direction less than 270, 250, 200, 170, something like that. Okay, so here you are accelerating in the north hemisphere on westerly heading. So when accelerating in the north hemisphere, you get a turn towards the north pole clockwise. So clockwise direction, all values increase. So what will happen? The magnetic compass will overread, increase, right? So it will overread and it will show an apparent turn towards the north pole. Next, a two-axis gyro which measures vertical changes, pitch up, pitch down, is so it's an artificial horizon. It has 2 degrees of freedom and vertical axis. Next, the altimeter consists of one or several aneroid capsules. located in a sealed case. The pressures in the capsule and outside the capsule are what? So this is your altimeter. This is the back side of your altimeter. Okay, behind the scenes. So you have this aneroid capsule here. Now these aneroid capsules have vacuum in them. Okay, so there is no pressure inside the aneroid capsules. In the capsules, they are vacuum, and outside the aneroid capsule in this instrument, you have the static pressure input. You have the static pressure surrounding the capsules. So the pressure in the capsule is vacuum, and the pressure outside the capsules is static pressure, which is fed from the static port. Okay, so option A. Next, item 19 of ICAO flight plan, endurance. So you can see here there is item number 19, endurance. Okay, there is this box in which you have to fill your flight endurance in terms of hours and minutes. That endurance is nothing but fuel endurance of your aircraft. How long the fuel in your fuel tanks is going to last. Okay, is going to be consumed. So that is fuel endurance of your aircraft. Now it's inclusive of your alternate fuel, diversion fuel, okay, but not reserve fuel. So you need not add any extra fuel like holding fuel or divergent fuel separately, because this endurance will be inclusive of trip fuel, alternate fuel, diversion fuel, holding fuel, contingency fuel. Okay, so this brings our lecture to a positive end. I hope you have understood all